Okay, I'm going to start by qualifying what I believe is the real-world drag coefficient, and then introduce the concept of wind average drag. I think that should really be reintroduce wind average drag, because the concept has actually been around for about 40 years. Maybe some people can remember that being introduced. Then I'll discuss some sensitivities and some test results from the test we've been doing. And finally, try and discuss why it's important to consider wind average drag. So throughout the presentation, I've called wind average drag CDW, just for convenience in here. So now, those of you with teenage kids, or maybe fortunate to still remember being a teenager, may realise that the parents' view and the teenagers' view of the real world can be quite often at loggerheads. Now, I don't want to get embroiled with an argument as to what actually the real world is here, but I'm going to, because the real world in terms of driving cars is very, very complicated, but I'm going to give you a very simplified view of what my view of the real world is. There are many different driving styles. You've probably seen those on the roads as you're driving around, and I'm going to try and eliminate these driving styles. So I'm picking a fixed vehicle velocity of 110 kph and with the wheels firmly on the ground. Then I'm also using a standard unmodified car. When the car leaves the factory, we've got no control over what the customer actually does to the car when they get it home. And believe you me, the customer doesn't always know best. So it's a standard car without any modifications, whether those from the customer or whether those actually modified from the OEM itself. And sometimes at JLR, we feel that our accessory department are doing their best to sabotage our best efforts with the aerodynamics department. We've gone here from a very sleek aerodynamic discovery at 0.4, and we've managed to increase it by 50%. But it's the basic shape that I want to consider, just as a standard car. So I'm taking into account the natural windy environment, but only insofar as light winds and not gusty winds. So not like yesterday with the extreme sort of weathers we had. And these are sort of typical weather systems, but not those extreme events that we can see in the picture here. So it's worth bearing in mind that these sort of events only occur less than 10% of the time, but they do make the headlines. So it's a standard car being driven in normal conditions. And this is where the modern wind tunnel can actually help us to obtain the data to determine our wind average drag. So I just want to touch on what the wind distribution in the UK is, and this actually applies really to the rest of Europe. In the UK and most of mainland Europe, the motorways run from north to south. And the prevailing winds tend to be in the south to the west quadrant, which therefore means that vehicles are predominantly being driven in a crosswind environment. So the motivation for this study was that I wanted to be able to quantify the effect of the ambient wind on drag and then be able to compare vehicle to vehicle. Now there are several wind average drag methods around, but I've picked on the MIRA method because it's the more comprehensive. The other methods tend to only use a fixed wind speed, whereas the MIRA wind method uses a range of wind speeds. Unfortunately, I can't find any papers to support the MIRA method, but safe to assume that if the late Jeff Carr would have been involved with the method and would have been responsible for some of the development. And if that is the case, then it'd be fair to say that it had been thoroughly researched and things would not have been given to chance. So the MIRA method assumes my simplified view of 110 kph as a vehicle speed, and then uses 7 weighted ambient winds from 2 kph up to 25 kph. And we're assuming then that the wind can approach the vehicle in any direction. So it's then using the calculation over the range of plus or minus 180 degrees. It's worth also bearing in mind that the truck industry in the US is already using the wind averaged drag data in their calculations for fuel economy. So I've tested 50 different vehicles, maybe slightly more SUVs than saloon cars, but there's a whole range of cars, both from JLR and all our other, for us, our competitor cars. And although the results I'm going to show you are actually tested on the fixed ground, because that's the wind tunnel that we have main access to at Myra, we have tested some of these vehicles on the moving ground, and the characteristics that I'm going to mention are the same over both the moving ground and on the fixed ground. So an experienced aerodynamicist should be able to get a range of cars and be able to say which has the lowest CD up to the highest CD. Maybe if some of the newer cars are a bit more difficult to determine, distinguish between them, but if you had a range of cars, then you should be able to have good confidence to put them in the correct order. But what happens when the car goes at yaw? We know that the drag goes up as the car goes into yaw, but by how much? Well, I dare say no one could really predict to say that car is going to have a lower CD at yaw than the next car. So we tend to find that, we know that the drag response at yaw is a parabolic response, but what happens if some of those vehicles have a very pronounced minima at the straight ahead, so they don't actually follow a parabolic response? So is this then where we can use the wind average drag to quantify the real world drag? As I've just mentioned, that the car is nearly always at yaw when it's been driven. So I've selected some of the saloon cars here, that not all vehicles have parabolic responses. Some of the vehicles have very pronounced drag minima at the straight ahead. So this phenomenon is becoming very common for a certain category of vehicles, and namely those which already have a very low CD at the straight ahead. But then, does it really matter? Should we really be concerned about that? Well, over the small yaw range, up to 5 degrees, and put it back into perspective, that 5 degrees is round about a 10 kilometre side wind at 110 kilometre vehicle speed, that we can see that for a parabolic response you can have between 2.5% and 4.5% increase in drag. But in the worst case, where cars have a very pronounced drag minima, the increase in drag can be as much as 10 or 11%. So I'm not going to try and explain why why the particular vehicles have this response. That's maybe for an academic study, but just to say these cars do actually have a higher drag at yaw. Now SUVs tend to have far less sensitive yaw response. There are a few that have drag minima, but they all tend to have what you would tend to expect. I'm not sure if this is down to just the side area being larger than on the saloon, or just that the base drag becomes the dominating of the overall drag. So we go from the minimum of around about 2.5% to a maximum increase at 5 degrees of around about 6 to 7.5%. So it's a lot less spiky yaw response. So going back to the saloon case, what I've tried to do here is look to see if, with this distinct pattern of very pronounced minima and those cars without the pronounced minima, whether that actually makes the difference. So here I've plotted wind average drag, take away the CD at the straight ahead, plotted against CD at 0 degrees yaw. Now, I'm not suggesting here that there's a shift changeover at a CD of 0.29, that the cars we managed to test were not necessarily the low drag derivatives of those particular models. So what we would know is that those line at 0.29 for the red crosses would tend to shift to the left. So those are the low drag cars. They have low drag cars in the stablemates, and they will tend to shift to the left. So is this as a result of cars being aerodynamically developed just at the straight ahead? Aerodynamicists strive to lower the CD, but the car is very at the straight ahead. But the car is very rarely in ambient wind that's at straight ahead or still. And we spend many hours. Aerodynamics spend many hours either in the wind tunnel or using the CFD. And I dare say that if a vehicle designer would give them a 10% reduction in CD, they'd give their right arm to them. But if all that benefit is then lost by the time you get to 5 degrees, then I think I'd be felt a bit hard done by. So the drag reduction is a primary driver to reduce the fuel consumption and the CO2 emissions. But if we know that the real world is different than this idealised case from the Windsor or CFD, then should we consider using that calculation in the fuel economy? The EU is actually introducing a new test procedure which is supposed to be more realistic for fuel economy. And I'm not going to go into the ins and outs of the WLTP. I'm sure there's far more qualified people here to enlighten us on the contents, but I'm just going to pick one aspect on there, which is affected by the aerodynamics. Now, the current typical driving cycle is we call it the NEDC, which is the new European driving cycle, but aerodynamics only has an influence in really the last 18%, where the vehicle is actually driven over 70 kilometres per hour. But this sort of driving cycle doesn't strike me as being particularly typical, maybe for city cars. And the new driving cycle, the WLTP, stipulates that CD must be measured with moving ground and with real rotation, amongst other things. And it does take into account a higher vehicle speed and for longer. So aerodynamics is now playing a bigger role in this driving cycle. But it still doesn't consider any ambient effects. And I wonder if that's really an opportunity that's been missed. So to conclude then, the CD measured in the wind tunnel or by CFD is very highly idealised, and it is certainly not that experienced by the customer. But the real-world drag coefficient then needs to allow for the ambient wind effects. And I think this is where, to my mind, the wind average drag can characterise a vehicle in the natural environment, and then we can use the wind average drag coefficient, incorporate that into any real-world fuel economy calculations. Okay.